Right now, if you were to ask a team of 5 really sophisticated AI agents to, write and test and debug a piece of complex code for you.
Like a really heavy multi-agent workflow.
Exactly. There is a very real chance that the system will basically fire its most vital lead engineer mid-task, just to make room in its memory for, like, a quick one-off Google search.
Yeah, which sounds insane, but it happens all the time.
It really does. Behind the polished chat interfaces we all use every day, there is this massive, totally invisible traffic jam happening.
And it's a traffic jam that is, frankly, costing the industry an absolute fortune. Just a fortune in wasted computational power.
Oh, yeah.
And it's only getting worse, right?
Yeah.
Because we are transitioning from, simple prompting to these really complex multi-agent workflows.
Which is exactly why we're doing this deep dive today. We have a brand new state-of-the-art paper from the Generative AI Foundation Chronicles. This just came out in May 2026.
Really fresh research.
Super fresh. It's called Hive, a multi-agent infrastructure for algorithm and task-level scaling.
Quite a mouthful.
It is. But, okay, let's unpack this. Because
Okay.
the mission for this deep dive is to figure out how we make multi-agent AI systems actually collaborate efficiently. Like,
Yeah.
without just throwing, racks and racks of incredibly expensive hardware at the problem.
Right, because that brute force approach, we were hitting a wall with it.
Fuck time.
To really appreciate what this new Hive infrastructure is doing, we kind of have to step back. We have to look at the history of how we've been scaling AI.
Right.
The researchers in the paper, they outlined 4 distinct paradigms of scaling. But for the last few years, the entire tech industry has basically been completely obsessed with only the first 2.
Right, so let's unpack those first 2.
Yeah.
Because I think that's what most people listening are probably familiar with. You have model-level scaling and system-level scaling.
Correct. So model-level scaling is the most obvious one, right? You want a smarter AI, you build a bigger brain.
Just add more parameters.
Yeah, exactly. You increase the parameter count from, like, 8 billion to 70 billion. You feed it trillions of tokens of training data, and, it inherently gets better at reasoning.
Right, that's when you see your GPTs and Claudes releasing their massive version updates every few months.
Yeah.
But eventually, you can only make the brain so big before you physically just can't run it anymore. Which I guess brings us to the second brute force method.
Right, system-level scaling. Now, this is purely about the physical hardware and how we actually serve the model to users.
Like the actual servers.
Yeah, you buy more GPUs.
Yeah.
You upgrade the deployment architecture. They use techniques like PD disaggregation or context parallelism.
Hold on, wait. Let's define those because they sound incredibly dense. What is PD disaggregation in plain English?
Sure. So PD stands for prefill decode.
Mm.
In a standard setup, the exact same GPU tries to read your prompt.
Which is the prefill part.
Right. And then it generates the response. That's the decode part. But reading a massive document takes a completely different kind of, like, computational rhythm than spitting out words one by one.
Oh, interesting.
Yeah, so PD disaggregation splits those jobs up. It assigns dedicated hardware just to read the prompts and completely separate hardware just to generate the text.
Okay, so it's kind of like separating the kitchen staff from the wait staff in a restaurant so they don't trip over each other.
That is a perfect analogy, yeah.
Okay, and then what about context parallelism? What is that?
That's for when a user uploads a massively long document, say like a 1,000-page legal brief.
Which people do all the time now.
Exactly. But no single GPU can hold that much context in its active memory. So context parallelism slices the document up. It distributes the pieces across multiple GPUs, and they basically talk to each other in real time.
Got it. Okay, so model scaling makes the AI smarter, and system scaling is like building wider highways so the hardware can actually handle the traffic. But if we are doing all of this, why are we still hitting this massive traffic jam you mentioned at the start?
Well, it's because we've largely neglected the infrastructure needed for the next 2 frontiers, which are algorithm-level scaling and task-level scaling.
Okay, let's focus on the algorithm side first, because if we are hitting a physical wall with how big we can make the models, and obviously we can't just buy infinite GPUs, how else are we supposed to make these things smarter?
By giving them more time to think.
Time to think.
Yeah. Algorithm-level scaling happens at inference time, meaning, the exact moment you actually ask the AI a question.
Okay.
Instead of forcing the model to just blurt out the very first answer that comes to its mathematical mind, you design an algorithm that forces it to explore multiple reasoning paths.
Right.
It drafts an idea, it critiques it, it backtracks, and then tries another route.
I've seen this. This is referred to as tree of thoughts, right?
Yeah.
You start with a root problem, and the AI branches out into different potential solutions.
Exactly. Tree of thoughts. And the paper uses a really fantastic, super high-stakes example to illustrate this. They talk about RTL program repair.
RTL.
It stands for Register Transfer Level. It's basically the code used to design actual physical silicon chips.
Oh, wow. Okay. So if an AI hallucinates a bad piece of code for, like, a random website, the site just crashes. Not a huge deal.
Right.
But if it hallucinates a bad piece of RTL code, you could be manufacturing millions of physically defective microchips.
Exactly. It's literally a billion-dollar mistake.
Wow.
Which is precisely why you cannot tolerate a single guess. The AI must use tree of thoughts. It makes guess number 1, it runs a verification tool, and if it fails, it has to go back up the tree and branch out to guess number 2.
Make sure it's right before it finalizes anything.
Right. It's highly effective, but it introduces this massive mechanical bottleneck. The authors call it cross-path redundancy.
Okay, wait, I'm trying to visualize this. What exactly is the AI doing that's redundant? Because if it's trying different guesses, isn't it technically doing new work?
You would think so, right?
Right.
But when the AI explores different branches from the exact same starting point, the underlying context is identical.
Right.
Because of that, the most probable next words it generates across those different branches are often identical too.
Wait, let me stop you right there. I thought developers already had a fix for this. Isn't there something called prefix caching?
Ah, yes. Prefix caching.
Doesn't the system just save the shared prompt so the AI doesn't have to reread the original question every single time it tries a new branch?
What's fascinating here is that prefix caching only solves half the problem.
Only half.
Yeah, it saves the past context, the prompt you gave it. But it does absolutely nothing to stop the AI from generating overlapping, totally redundant tokens in the future branches.
Oh, I think I see what you're getting at. If branch A and branch B both start their answers with the exact same 5 words,
Yep.
the AI is actually doing the math for those 5 words twice, completely from scratch.
Yes.
Yes.
Every single time. And to understand how heavy that math actually is, consider the model they reference in the paper, which is DeepSeek v3.2.
Okay.
It has 62 layers in its neural network. So to predict just one single word, the model has to push data through all 62 layers just to calculate the logits.
Logits, right. Those are the probability scores, right? Like the mathematical breakdown of what the next word is most likely to be.
Exactly. So the logits might say there's a 90% chance the next word is therefore, a 5% chance it's however, and so on.
Got it.
Calculating those logits across 62 layers requires an immense amount of matrix multiplication. Now imagine an AI doing that massive calculation for the exact same sequence of words over and over, just because they're technically in different branches of its thought process.
Oh my God.
It is a staggering waste of computational time.
That sounds incredibly frustrating. It's like we've given the AI a GPS to find the best route, but the GPS makes it recalculate the entire map from scratch every single time it takes a slight detour.
Exactly.
So how does Hive actually fix this?
Hive introduces its first major back-end innovation, which is called the Logits cache. Instead of throwing away those heavy probability distributions after generating a branch, Hive actually saves them.
Okay, but save them where? Because I know GPU memory is incredibly expensive, and it's usually completely maxed out just holding the model itself.
That is the genius of it. Hive stores the Logits cache in the CPU's main memory, not the GPU.
Yeah, let me play devil's advocate here for a second.
Sure.
Moving data between a computer's main memory and the GPU is notoriously slow. It's limited by the PCIe bandwidth. I've heard it described as, like, trying to suck a swimming pool through a straw.
Yeah, that's a fair point.
So if the GPU has to constantly pause and wait for the main memory to hand over the cached logits, doesn't that just defeat the whole purpose of saving time?
It would, absolutely, if it were waiting.
Hmm.
But Hive uses asynchronous background tasks.
Oh, asynchronous.
Right. It anticipates what the GPU is going to need next, and it uses a background thread to prefetch the data. It basically sneaks it over the PCIe bottleneck while the GPU is busy doing other math.
Wow.
Yeah, so by the time the GPU actually needs the cached logits, they're already there.
That is incredibly clever. Okay, so once the AI has the cached logits, how does it use them to speed up its thinking? Because the paper mentions 2 specific methods, right? Stepwise sampling and hotspot sampling.
Yeah. Stepwise is the simplest one. The AI just strictly follows the cache trajectory token by token.
Okay.
It essentially replays the saved logits and samples from them until the new branch finally diverges from the old one and requires new math.
But the downside there is that branches usually diverge pretty quickly, right? Like you might only save a few words of computation before you're right back to doing the heavy lifting.
Exactly. Which is exactly why the second approach, hotspot sampling, is where Hive really shines. The researchers leaned into a known quirk of how AI generates text, which is that uncertainty is not spread evenly.
What do you mean?
Well, most of the time the AI is like 99% sure of the next word. But occasionally it hits a moment of high entropy, a spot where it is genuinely torn between 3 or 4 radically different paths.
So hotspot sampling specifically targets those moments of uncertainty.
Yes. Hive calculates an important score for every single step based on its entropy. And it identifies what they call spot nodes, which are those highly uncertain pivot points.
Okay.
So when the AI goes back to try a new branch, hotspot sampling only recalculates the math for those specific uncertain moments. For all the stable, obvious words in between, it completely skips the 62 layers of math and just uses the cache tokens.
Oh, that's like reading a dense textbook. Stepwise sampling is like rereading an entire chapter just to find one specific fact you forgot.
Right.
But hotspot sampling is like having a perfectly highlighted textbook where you just skim past all the obvious filler and only pause to think deeply at the highlighted sections that actually require analysis.
That is a remarkably accurate analogy. And the performance data really reflects how powerful that is. The researchers tested this on the Hugging Face 24 game dataset.
The 24 game, wait, that's the math puzzle where you get 4 random numbers and you have to use basic arithmetic to make them equal 24. Right.
Yes. And it's a perfect test for tree of thoughts because the AI has to constantly guess, realize a path won't equal 24, backtrack, and try a completely different combination.
Right, lots of branches.
Exactly.
Yeah.
Now, when using stepwise sampling, the Logits cache achieved a respectable speedup of about 1.10x. But with hotspot sampling, where it's skipping the obvious math, the speedup jumped to a massive 1.76x.
Almost twice as fast.
Yeah.
Purely by stopping the AI from overthinking the easy parts.
Yep.
Okay, so that completely solves the algorithm bottleneck. But earlier, we talked about a fourth scaling paradigm, which was task-level scaling.
Right.
What happens when we zoom out from a single AI thinking deeply, and we look at a whole team of AI agents working together?
This introduces an entirely different and frankly much messier infrastructure problem. To benchmark this, the researchers used a multi-agent workflow called R3A, and again, this is focused on that high-stakes hardware verification we talked about earlier.
This workflow uses 5 specialized agents, right? Walk me through what this, digital corporate department actually looks like.
Sure. You have the decision agent, which acts as the project manager, kind of planning out the steps.
Okay.
You have the patcher, which writes the actual code drafts. The viewer, which reviews slices of the code for errors. The summary agent, which compresses massive logs of context. And finally, the searcher, which occasionally retrieves external knowledge.
Okay, so 5 agents with very, very different jobs. What happens when you put them all on the exact same server?
You run into a massive bottleneck called heterogeneous runtime characteristics.
In plain English.
In plain English.
Yeah.
They do not all act the same, but the system treats them like they do.
How so? What's the difference?
Well, profiling the R3A workflow revealed that the decision, patcher, and viewer agents are incredibly hot. They do all the heavy lifting, they're constantly talking back and forth, and they take up over 70% of the total token volume.
Okay, so they're the workhorses.
Exactly. Meanwhile, the summary and searcher agents are cold. The searcher might lie dormant for 10 minutes, wake up, pull in a massive amount of external data, and then just go right back to sleep.
So what's the issue? Don't current systems just give the hot agents more resources?
They absolutely do not. Current inference engines are what we call agent agnostic.
Oh, no.
Yeah. They have no idea that 5 different agents are collaborating. All the engine sees is an incoming stream of text requests. So it manages its memory, specifically the KV cache, which is basically the AI's short-term scratch pad using really generic blind rules. The industry standard is LRU, or least recently used.
Least recently used. Meaning, if the short-term memory is completely full and a new request comes in, the system just deletes whatever data hasn't been touched in the longest amount of time to make room.
Exactly. It operates entirely on chronological recency. It has zero concept of importance.
Wait, I think I see the disaster here.
Yeah.
If the vital decision agent finishes a major planning phase, and then the dormant searcher agent wakes up to do one massive memory-heavy query.
Yep.
The system is going to look at the memory, see that the decision agent hasn't been active for a few seconds, and literally delete all of its context just to make room for the searcher.
Yes. That is exactly what happens. And because this is a collaborative loop, a few seconds later, the workflow will inevitably call upon the decision agent again. but its memory is gone.
Oh, man.
So the system has to experience a cache miss and recompute the decision agent's entire history from scratch, which just grinds the whole operation to a halt.
So going back to my intro, it really is like a company firing its lead engineer to give an intern a desk.
Pretty much.
And it's actually worse. It's firing the lead engineer's memory of the project. When the engineer comes back, they have to reread the entire project history from page 1.
Right.
That is a deeply flawed way to run an infrastructure. How does Hive fix this blind spot?
Hive completely abandons the generic LRU policy. It introduces what they call agent-aware scheduling. So it elevates memory management up to the agent level, dynamically calculating a contribution score for every single agent in the system.
So it basically forces the agents to prove how important they are.
Exactly.
What's the math behind that? How do you actually calculate a digital worker's value?
Hive borrows a brilliant concept from game theory called shapely values.
Shapely values. I've heard of this in sports analytics. It's like calculating a basketball player's plus-minus stat, right? Like figuring out exactly how much worse the team would perform if you removed that one specific player from the court.
That is exactly how it works. Hive adapts this into a contribution score made of 2 parts. The first is intrinsic utility.
Okay, what's that?
This measures how much raw work the agent is doing in isolation. Hive tracks how often the agent is invoked, the sheer volume of tokens it processes, its cache efficiency, and its concurrency, meaning how much sustained pressure it puts on the GPU. If an agent is constantly grinding out code, its intrinsic utility skyrockets.
Makes sense. Reward the hardest workers. But in a multi-agent system, raw output isn't everything, right? Like, what about the project manager agent who just coordinates the others?
That is captured by the second part of the score, collaborative utility. Hive actually maps out a bidirectional graph in real time to track how much reusable cache state an agent generates for its peers.
Oh, wow.
Yeah. So if Agent A creates a ton of context that Agent B and Agent C rely on to do their jobs, Agent A gets a massive boost to its collaborative utility, even if it doesn't output many tokens itself.
This is fascinating, but I do see a potential risk here.
What's that?
If you're judging an agent's right to keep its memory based purely on its past behavior, what happens when an agent's role changes? Like, say, the cold searcher agent suddenly becomes the most critical part of a totally new phase of the workflow. If its historical score is too low, will it just be starved of memory and crash the system?
The researchers anticipated that exact trap. The scoring is not permanently fixed. Hive uses a sliding window to update the runtime profiling during every single round of the workflow, so the scores are constantly adapting to changing behaviors.
That's smart, but how does the backend physically know which agent is which? Like, if it just sees incoming text, how does it track these shifting scores?
Through an incredibly elegant front-end design, Hive registers the individual agents just like Python coroutines.
Meaning it gives them, like, a digital ID tag?
Essentially, yes. In programming, a coroutine is a function that can pause its execution, hand control back to the system, and then resume later right where it left off. By registering agents this way, Hive attaches a persistent identity to their memory streams.
Oh, I see.
So the backend scheduler isn't blind anymore. It always knows exactly who is requesting memory, and it adjusts the Shapley values dynamically.
So the system is constantly running an invisible performance review on the agents.
Exactly.
Did this actually solve the traffic jam in the R3A benchmark?
The results were phenomenal. By prioritizing the KV cache of high contribution agents and demoting the one-off queries, Hive reduced the hotspot cache miss rate by 33% to 51% compared to standard LRU baselines.
A 50% drop in cache misses. That's huge.
Yes, in their 21-round benchmark, this literally saved tens of thousands of tokens from being wrongfully evicted and mathematically recomputed. Hive aligns the memory residency with the actual structural importance of the team. It preserves the thoughts that matter most.
Which translates directly to staggering amounts of time and compute costs saved.
Absolutely.
All right, well, let's bring all of this together. For you listening, the core aha moment of this deep dive is realizing that the future of AI isn't just about waiting for OpenAI or Google to release a slightly bigger brain, or waiting for NVIDIA to build a slightly faster chip.
Right. The real bottleneck and the real solution lies in structural efficiency.
Exactly. It's about using Logits caching with hotspot sampling to stop the AI from doing redundant 62-layer math when it's exploring different thoughts. And it's about agent-aware scheduling, using game theory to manage the memory of complex AI team dynamics instead of just relying on blind chronology. As you start deploying your own AI workflows to prep for meetings or summarize complex fields or code applications, the invisible infrastructure making those tools actually fast and usable will rely on the exact concepts we just unpacked.
And if we pull back and look at the philosophical implications of this infrastructure,
Oh.
there is something profoundly interesting about how Hive operates. Yeah. It judges agents on their collaborative utility to decide whose memory survives. If future computing infrastructure operates this way on a global scale, are we accidentally creating digital micro-societies?
Wow.
Environments where AI agents must constantly compete to prove their usefulness to the collective, just to stay alive in the system's short-term memory.
A digital survival of the most collaborative. That is a wild thought to leave on. Thank you so much for joining us on this deep dive into the Hive architecture. Keep exploring, keep questioning how your tools actually work, and as always, stay insanely curious.